I'm a postdoc with the USGS in NGCHOC, the National Geospatial Technical Operations Center. And within that, I'm in CGIS, the Center for Excellence in Geospatial Information Science. And there's acronyms above that too, if you know, it's a maze. But I work on building tools for automated characterization of hydrographic features. And so I'm going to talk about a little bit of that work. We're doing new work, so the opportunity to present this is timely. Let's see here. I'm going to try to use this as a laser pointer. Good. Great. Many factors contribute to meander geometry. Sinuosity, including surface composition, so that can be vegetation, the type, how close to bedrock you are, alluvium composition, and is often used in hydrologic and ecologic classification. The most common way to describe stream bend complexity is, most common often used is sinuosity, defined as the ratio of the total stream length to end-to-end stream length. And so quantities other than this would be useful for discriminating between various degrees of complexity. Determining meander geometry has been discussed for decades, including the correlation with channel width. Williams, for instance, looked at streams with sinuosity greater than 1.2 and only in alluvium material. And so there's clearly a trend, you know, in the 2.5 times the channel width as a ratio for meander geometry. But it's not a clear trend, and it's not likely useful for modeling amongst all different stream types, which is what we're looking at, is nationwide coverage. The NHD currently has a lot of attributes, and sinuosity or better defined bend geometry would be a useful attribute. So you guys are familiar with the Richardson plot. We've seen that already. But just as a primer, no, I'm behind, sorry. As a primer, as you change the length you use to measure a feature, the length of the feature changes. So moving from step size 1 to step size 2, your feature gets smaller. And the result, when you plot this with various step sizes and feature sizes, you get the Richardson plot, which is done those measurements on a log-log scale. And here is a coarse Richardson plot with about 12 measurements of the Cannonball River in the Dakotas. This is the southern end here. I have my mouse pointer. And so what we see is Mandelbrot used this, confusion between pointer and clicker now. Use this to determine the 1 minus the slope is the fractal dimension for geographic features. Other people have looked at where the line is not asymptotic to 0 or slope of 0, but still this is one dimension and could miss complexity in stream features. So we are looking at scale-specific sinuosity, and this is a partial sinuosity metric defined as -1 times the slope of the Richards plot at individual step sizes. Also, the area under the S3 curve is equal to the log of sinuosity, which can be shown with some derivation, and therefore the metric characterizes the relative complexity and preserves the original sinuosity metric. I'm reading because I have the tendency to dwell on slides and would not make the time. So here we have some examples. We've been testing the comparison of the S3 to Fourier analysis, and in this we generated some uniform curves with a given wavelength and amplitude. You probably can't see here, but this is a wavelength of 150, and they get more complex using different wavelengths and amplitudes down here. And so these are the Richardson plots for those, and what you see is when you have a regular uniform curve pattern, you get these sawtooth patterns that arise amongst the points, and then with more complexity you get tighter and tighter grouping of the points. And also the slope becomes more gradual when you have more complexity. This has been shown by others. So here we have the resulting S3, so we took the top points, which is equal to, the area under those top points is equal to the log of sinuosity, so it preserves that sinuosity metric as well. and also it gives a better example or a better metric for distribution of contributing wavelengths. And a big part of this is for comparison between streams. I'll talk hopefully a bit more about that at the end if we have time. We expect the peak to go down, so the peak is slope. The S3 is the slope times -1. So we expect that peak to be lower with more complexity. You get smoother slopes, but we see here we have this rise on the right, and that's likely due to sample interval, and there's some other thing, the way we did it. The way we changed the step size is multiplicative, so their spaces are wider towards the end. And these are all things we're playing with to optimize. Here's 3 natural features, and so you can see the Richardson plots. These are more complex features, so your tight groupings of your top and bottom points. All curves that we found diverge between the top and bottom points at the tails as you get to the length of the actual feature, and that's just the step size going in and out of phase with the curve, with these measurement or feature length curves. So you see very little drop for the Reese River because it's pretty straight, but you also see where the complexity likely happens, and a dominant curve geometry for the Osage River. And this is resolved well in the resulting S3 plots. In conclusion, S3 is a partial sinuosity metric at specific scales. Fourier fitting has been suggested by others for geometry measurement, but our test suggests it's noisy with more than 2 contributing frequencies, and it's not suitable. Preserving cartographic features through changes in scale is an important consideration for the NHD. And hopefully the S3 metric can be useful for that by attaching it from different scales. So we're envisioning taking this measurement and using it at different window sizes. So you move along an NHD feature, and the S3 will change along that feature. Different ways to attach that S3 metric to an NHD feature, so that it could be taken into consideration or simply preserved in generalization. We're continuing to look at smoothing of points and how to deal with that sawtooth pattern that arrives, as well as optimal step size increments and transitions from hydrologic meanders to geologic meanders, or as Dr. Wu mentioned, potential scale breaks. We are also looking at methods for comparison of the vectors, so treating the S3 as a vector and comparing it between other streams, possibly across the country, maybe within regions, different sizes. And one thing we've been looking at is at the cosine theta comparison. It's a normalized dot product, and this is a sorted dissimilarity matrix. And so you have the streams is mirrored about the diagonal axis. And so it just shows how similar one feature is to all the other features in the group. That we could talk about that for a while. And then also correlation with other landscape parameters is something else we're looking at. And that is all I have.